Welcome back to HackCode. In this video, we're tackling an essential problem for coding interviews, combination sum 4 from LeetCode. This problem is great for learning dynamic programming and recursive backtracking. We'll explore three approaches: naive recursive approach, recursive backtracking with memoization, that is top-down, and dynamic programming bottom-up approach. Let's break down the problem step by step and understand how the solutions work. So sit back, relax, and let's dive in. So what is problem statement here? Given an array of distinct integer nums and a target, return the number of possible combinations that add up to a target. Okay, the test cases are generated so that the answer can fit in 32-bit integers. So basically we don't need to care about the overflow. Let's look at example one that would give you more idea about the question. Okay, so here in input the nums is given as 1, 2, 3 and the target is 4. So here the output is 7. What does the 7 represent? This is just the number of possible combinations that we can make 4 out of these 3 numbers. Okay, so first combination is what? Is just the same 1, 1, 1, 1. Okay, and next is what? We can make from 2 ones and 2. Okay, next is 1, 2, 1. So basically here this is a permutations, right? So this is 1, 1, 2 and the permutation is what? 1, 2, 1. Okay, and next is we have 1, 3. The permutation of this is what? 3, 1. Okay, and next is 2, 1, 1. Okay, so basically this is the permutation of this one, and next is 2, 2. Note that different sequences are counted as different combination. So basically here we see, right, this is one combination and this is another combination. So basically this different sequences would count to a different combination. Okay, and the key is here we don't have 2 repeated for twice because this is a single combination, right? So even though if you repeat like another time 2, that is a duplicate way. So we don't do that. So basically we take the unique permutations. Okay, in example 2, nums is given as 9 and the target is 3. There is no way we can make 3 from 9, right? So that's why we output 0. What are the constraints here? The nums length is in the inclusive range of 1 to 200. Okay, the nums of 5 is in the inclusive range of 1 to 1000. All elements of nums are unique. Okay, and the target is in the inclusive range of 1 to 1000. Okay, so basically the main theme of giving constraints is we have to come up with the solution which is accepted. So the solution would be accepted only if we solve this in a 10 power 8 operations per second. Okay, so more than that it would be time limit exceeded because a computer can perform 10 power 8 operations per second. So keeping this in mind, we have to form our solution. This is the boilerplate code given, wherein we have a combination sum 4 method, and this takes nums. Nums is nothing but a list of integers we have here and the target. Okay, and it is the integer. This integer is what? The number of possible combinations that add up to the target. Okay, so let's look into the solutions. Before we get started, I want to remind you about our exclusive blind spot info post. This carefully curated collection covers essential coding interview problems to help you master the most common patterns and excel in your interviews. Whether you're prepping for FANG level interviews or just sharpening your problem solving skills, these problems will ensure you're ready for anything. Even if the exact questions aren't asked, they cover all the important patterns. So be sure to check out our playlist and stay ahead of the competition. So firstly, let's look into the recursive approach. So what is our intention here? We aim to calculate total number of ways to reach target by subtracting elements from it one by one. This approach explores every possible combination exhaustively. So this is just like the depth first search. Okay, so basically what the intention is, so we have this target 4, right? So each time we go to the loop for this nums and then we subtract 1, 2, 3 from it. Okay, so as we subtract one element, that is 1, we send again to the helper function, recursively call the same function again and again. So you'll get the more idea once we look into the code. For that, let's look at the algorithm. So what is the algorithm here? In step 1, so it's very obvious that we have to define helper function to recursively explore combinations starting with the target value. Okay, so firstly we would require to define some helper function. We name it helper only here. Okay, in step 2, if the current target is 0, it means a valid combination is found, so return 1. So what does it mean? So basically when we keep on subtracting in numbers and get a 0, that means that we went through a valid path which could make up to the target. In that case, we can return 1 saying this is a valid combination we have. Okay, so this accounts to that combination. Also keep in mind that recursive functions should always require a base case, else it would keep on calling itself and it would get a recursion depth exceeded error. Okay, so for that cases we should define our base cases properly, else we would face that recursion depth exceeded error. Okay, in step 3, if the current target is negative, it means the combination is invalid, so return 0. So this means that we reached a point where we can't make a target out of the given numbers. whatever the path we went through, that is invalid. Okay, so that case we have to return 0 because we don't form a combination, right? So that's why. So in step 4, for each number in the list, reduce the target by that number and recursively compute the number of phase for that reduced target. Sum up all these values to get the total number of phase. So basically, as we discussed, we have to reduce the target by the current number, okay, and we have to recursively compute the number of phase for the reduced target. So firstly, if you consider, we have numbers 1, 2, 3 and the target is 4. So we have to form 4 out of these 3. So firstly, what we do, we subtract 1 from this and 2 from this and 3 from this. So if we subtract 1, what we get is 3, and here we get 2 and here we get 1. So again we do subtract 1, 2, 3 from these things recursively, right? So here we subtract 1, 2, 3. So if subtract 1 from 3, it would be resulting 2. This would be resulting 1. This would be resulting 0. So the moment it returns 0, it is a valid path we have, as we discussed, right? So here 1, 3 were one of the possible combinations. And similarly here we do subtract 1, 2, 3. So here from 2, if we subtract 1, it would be 1. So from 2, if we subtract 2, it would be 0. And from 2, if we subtract 1, it would be -1. So this is the invalid path. So what are the valid paths we have from here? 2 is a valid path and this is the invalid path. So let me just write a valid path here. So here 2 is a valid path. So likewise, our stack grows on. So we recursively keep on comparing this. So wherever we get 0, that means that it's resulting in a valid path we have. And wherever we get -1, you saw it, it's evident that it is not a valid path. So that's why we written 0, saying that this is not counting to our combinations. Okay, so that's the idea, guys. So now let's look into the code. So this is just what we discussed, but in form of code, very simple. So firstly, we define our helper function, so which takes the remaining. So remaining is what the target we have. Okay, I kept it remaining because each time we subtract, right, as we discussed here. So that's the idea of keeping as remaining, not target. Okay, so if remaining is equals to 0, that means that we found a valid combination. So we return 1. As we discussed here, if remaining is 0, that means we found a way where we can form a target out of this given numbers we choose. So that's why we return 1, indicating the path we found. Okay, so basically this is the combination we have. And in the case where remaining is less than 0, that means that it's an invalid path we considered. So here if we take 2 and 3, it's invalid path, right? So that's why we had to return 0, saying that it's not contributing to your path and the value of that path is 0. And next we explore all possible combinations by subtracting numbers, as we discussed here. So for each time we subtract 1, 2, 3, right? So that's why we go in a loop here. So here we have to keep track of the total number of phase, right? So that's why we initialize a variable here, total number of phase equal to 0. And for num in nums, we're just adding the result of the helper function, which takes remaining minus num. So whatever remaining here, we subtract the current num and we add the result of this particular function called to the total phase. So that way we are summing up our combinations. Okay, so basically helper returns the combination of that particular path, right? So for this case we return 0 and for this case we return 1. This case also we return 1. So all that should be summed up, right? So that's why we are summing up here. Plus is equals to helper. That means that this is just a shorthand form. This is in longer form we can say that total base is equal to total base plus helper of remaining minus term. But this equals to minus is just a shorthand form. Okay, so at the end we just return the total base. We are just interested in total number of ways, so that's why we return the total ways. Okay, so this is the helper function we have, and then initially we make a call to the helper function with the target. So that's why we just return the helper function of target. This helper function of target would return the total number of ways we have. Okay, and this recursion stack starts processing once it reaches the base case. So base case is what here 0 or -1 we have, right? So we define the base case here. So from that base cases, it would start processing. Okay. So what are complexities? Our time complexity is n power t, where n is the number of elements in the array and t is the target. So how do we get this? So basically here, if you see here, we are making 3 recursive calls because we have number of element as in nums is 3. So we make 3 calls. That's for what? One particular combination. So here, if you consider this combination, we have to go till what? How many times? T number of times, where t is the target, right? So basically our sample space would be in the range of 0 to t only. Okay, so t is a target. Okay, till that range we have to explore all possible combinations of forming this from the all given numbers. So taking nums length as n, we would be doing this computation till what? T times. So that's how our time complex become n power t, which is the exponential. Now the space complex is O of t due to the recursion stack. So basically the recursion stack maximum it can maintain is till O of t. T is what the target here. Okay, so after that it would keep on popping up. That's why it's O of t. Okay, I got the code ready here. Let me try running this. So this is the actual solution for these two cases. Let me try summoning this. So we see the time limit is exceeded and only 9 out of 16 test cases were passed. This is because the solution is having an exponential time complexity and this won't be scalable for the larger inputs. So that's why we had to reduce the complexity. So let's look into the optimizations. Let's look into recursive stack, which will help us to optimize the solution. So I consider the example one wherein we have numbers 1 to 3 and the target is 4 and the output is 7 here. So this is just a subset of the recursive stack we have. So firstly we make a call with 4, right? That's why I represent helper of 4 here, and nextly we make 1 to 3 subtractions, right? So that's why here we subtract 1 and we call helper of 3, and we subtract 2 we call helper of 2, and we subtract 3 we get helper of 1 call. So here this is a subset of the recursion stack, so that's why we don't have everything here. So if you need to consider the whole recursion stack, this would be what 3 into 3 into 3 into 3, so 3 power 4 calls. That would be what it's 81 calls, which we can't represent, right? So that's why I just represent the subset of the recursion stack, but that would give a clear idea. So if you take a closer look, here we are making the repeated calls. So helper of 2 is called for twice, and helper of 1 is called for what? Thrice, and helper of 0 as well is called for thrice, and helper of -1 is called for twice. So what you notice here, so basically no matter how many times we make a call, this result is always trivial. It's always same value would come, right? So why we need to compute again and again? That means if we compute once and we store this result somewhere, we can use this other time, right? So that's the idea, guys. I'm talking about the memoized version, which is the top-down dynamic programming. So this is just like once we compute the sub problem, we will use that to solve the bigger sub problem. Basically, we compute the result and we store it in our cache. And next time we get the call for the same number, that is helper of 4. So here if we get a call for 4, we can just look in our cache and return it. So that's how we saving our computation time. That will help us optimize the solution. Okay, so let's look into our approach 2, which is recursion with memoization, that is top-down dynamic programming approach. So what is the intuition here? This approach enhances the naive recursive method by avoiding redundant calculations. It uses a memoization table to store previously computed results for each target value. Okay, so just a heads up. So later point of time in the video, I'll show you how to convert this recursive code into a memoized version with just one liner change. But to understand that, learning this algorithm is essential. So let's look into this algorithm, okay? So in step 1, define a helper function to compute the combinations recursively. Use a dictionary to store previously computed results for the target values. So basically here, this is same as the previous approach, but we just use a dictionary to store the previously computed results for the target values, okay? This is the additional step we're doing from the previous approach here in this step 1. And in step 2, this is just the same base case. If the target is 0, we return 1 as it represents the valid combination. And in step 3 as well, if the target is negative, we return 0 as it's invalid. Okay, this is the same step. In step 4, if target is already in memo, we return the stored result. So this is the additional step we have in this approach. So basically, as we discussed, if the target is already computed, we just return this stored result. Okay, so that's the idea, guys. That's how we're saving our computations. In step 5, otherwise, compute the combinations by recursively reducing the target with each number, store the result in memo and return it. So basically this is same as a previous approach, but we just store the result before returning it. That's the idea. So let's look into the code. It's very simple. So here we have just some minor changes, but as I mentioned, I will tell you with just one line of change how can we convert this into this version. Okay, so here we initialize the memoization table, which is nothing but our dictionary. Okay, and next we have the recursive function. So this is almost similar to the previous approach. So these two base cases remain same, and here this is where the difference. Okay, so if remaining in memo, we just return the memo of remaining. So this is how we're saving our computation. Okay, next step, this is same. So here there is a difference. Memo of remaining is called total base. So once we compute for the current recursion, we store that value in the memo of remaining. Okay, and then we return the total base. So basically before returning, we store in our memo. So that's how when the next call comes, we can return from the memo itself. Okay, so that's the idea, guys. So here there's just an additional caching layer. Okay, so similarly here also we just return the helper of target. Okay, so what are complexities here? The time complexity is O of n into t, as each target is solved only once for all numbers. So as we discussed, our sample space only till what target times, right? So we just need to see if we can make this target from the given numbers. So if we have n numbers, we just need to see the possibility of getting this target from the n numbers. So it is n into t. So we have this number of combinations and we're trying this combination only once. So that's why it's O of n into t. Okay, The space complexity is O of t for the memo dictionary and the recursion stack. So here actually if we consider this recursion stack, as I mentioned before, it would take O of t space, and after that it would keep on popping and solving the recursion. Additionally, our memo dictionary should also require some space, right? That is also O of t. So till target it will store. That means the space required for this memo depends on the target we have, right? So if you have a target of t, then it would have the space of t. So here the total space complexity is 2 O of t. But this is an ignorable constant, so that's why it is O of t, okay? So now let's look into how do we convert this in Memoization with just one line of change. We just need to add rate of cache. This is the annotation we have, okay? So let me try summing this. So we see that this accepts solution now. So how did this get accepted? So basically here rate of cache exactly does what our dictionary does, okay? So firstly, it computes this helper function for a particular remaining, and next time if the call comes to the same remaining, it would just look in the cache and return it. Okay, that's the idea, guys. So now I got the code ready for the memoized version with table. Let me try running this. So this acts solution with the 3 test cases. Let me try summing this. So this acts solution for all the test cases and beats 83% of users. Cool, right? Approach 3, iteration with tabulation. This is a bottom-up dynamic programming approach. What is the intuition here? Instead of solving the problem recursively, we build the solution iteratively. So this is the iterative solution rather than the recursive solution. The key insight is to compute the number of ways to form target from 0 to the given target using previously computed results. So basically here also we will be using the previously computed results, and we will be computing the ways to form a target from 0 to the target. So we will be considering all the way from 0 to target. Okay, so that's the idea, guys. So let's look into algorithm. So create a DB array where each index represents the number of ways to form the target. So here the target could vary from what 0 to t. So if t is what they given, our targets would be varying from 0 to 7. Okay. So for that indices we have to fill it. Okay. In step 2, for each target from 1 to the given target, iterate to the numbers in the array. So basically we have to iterate and then only process, right? So that's the same step here. So in step 3, if the current number can contribute to the target, that is, it doesn't make the target negative. So in that case, we add the number of ways to form the remaining target, and that is current target minus the number to the current target. So it's similar to the previous approach only. So here what we are saying is, so firstly as we discussed, we'll be forming a DP array. So here we should be having the indices all the way from 0 to t. So here if we consider t is equals to 4, our DP array should be of length 5. In that case only we will get the index still 4. So let me just create a DP array like 0, 0, 0, 0, 0. This is our DP array. So firstly we'll replace our base case, which is 1 here. Okay. So next for each number. So here basically if we subtract this each number from 4, that is like firstly we subtract 1, and next we subtract 2, and next we subtract 3. So if this doesn't go negative, what we need to do, we just need to add the value of dp of t minus num. So here t is what? Current target. So current target, if firstly we start with 4, and t minus num is what? T minus the particular num we have, dp of 3. So what does dp of 3 stores? So it basically stores the number of combinations to make the target 3. So that's what, guys. So basically here we reusing this ways we have for 3, and then we adding that to the current target value. Okay, so it's just that we reuse our results. Okay, so now the formula is what? dp of 4 is equals to dp of t minus num plus dp of 4. So basically to the current value we'll be adding to the t minus num. So likewise, like we have the nums varying, right? So that's why we keep on adding to the current target, which is 4. Okay, that way we'll get all possible combinations which would make up to 4. Okay. Step 4, at the end the value of the given target in the DP array represents the total number of combinations. So basically here we have to return the last element value from the DP array. Last element value is what? It's nothing but the total number of ways to form the target from the given integers. Okay, so that's why we have to return that. So let's look into the code. So firstly here we insert the DP array. DP is equals to 0 into target plus 1. What does this make? So basically if you're not aware of the syntax, if you just multiply 0 with 1, we get only 0. If you multiply 0 with 2, what we get? We get the list of length 2 all filled with zeros only. So basically this represents the total length we want, and this represents the element which we want to duplicate. Okay, so that's the idea, guys. Next is our base case. That is only one way to form the target 0. So that's why we fill dp of 0 with 1. And next we build the solutions iteratively. So here we consider the t in range of 1 to target plus 1 because this is the exclusive range, right? That's why we do plus 1 to have a target included. So our t would be in the range of what, 1 to target. Okay, so that's how we get the target included in our range. Next we iterate into the nums. So for num in nums, we check if the number can contribute to the target. A number can contribute to the target only if the target is greater than or equal to num, right? So that's why we check if t is greater than or equal to num. So in that case only this num can form that particular t. Okay, so that's why we just have this check. And next here we're just adding the waste from the small target. This is similar to previous approach. In previous approach as well we are doing this total waste equals total waste plus helper of remaining managed num. So on the similar lines here we're just going via iteration fashion. So here what we are doing is we're trying to get all the waste from the small target. So basically let's take the example of target is equals to 4 and we have nums as 1, 2, 3. So in this case what is this dp of 4 holes? This dp of 4 holes the total number of ways to form that particular target, which is 4. Okay, is equals to dp of 4 plus. So basically why we are doing this plus? This is because we have to get all the possible ways of forming this from the 1, 2, 3, right? So that's why we have to do plus, because each time it has to be addition, right? So there's a variable part here. We have to form this from the small targets, which is what, dp of 4 minus num, which is 1 here. So dp of 4 minus 1 is 3 and this is one way, and next is what, dp of 4 minus 2, which is 2, and next is dp of 4 minus 3, which is 1. So basically for this 3 as well we would have explored the possibilities of making it from the 1, 2, 3. So we are starting from the 1 right here. So from 1 we explored till target. By the time we reach 4 we would have explored the possibilities of making 3 from the all the numbers we have. So we're just using this value to bring out the 4. Okay, so basically it would give us all possible ways we get 4 from 3, and then this what, and this gives the all possible ways we get 4 from 2, and similarly this is from 1. Okay, so that's the idea guys. We just need to add the ways from the small target. And finally we written our dp of target, because dp of target holds the number of ways to form the target from the given numbers, right? So that's why we written the dp of target. So what are complexities here? The time complexity is O of n cross t. This is same as previous approach, right? So basically here we have n cross t combinations. So here that means we are just exploring the possibility of forming each t from each n. Okay, so that's why it's O of n into t. Okay, the space complexity is O of t for the dp array. So basically here we initializing the dp array of length t plus 1, right? So this 1 is very negligible in front of t and it is just O of t. And also if you notice here we don't have any recursion stack, so we don't have any other extra space of O of t, right? So it's optimized in terms of space when compared to previous approach when we had 2 into O of t space complexity, but here it is reduced to only O of t. Okay, so I got the code ready here. Let me try running this. So the success solution for the two cases, let me try summoning this. So this splits almost 80% of the users. Cool, right? And this is wrap and solve the combination sum for using 3 different approaches. If you found this breakdown useful, drop a comment below and share your thoughts. Don't forget to like the video, spread the word to your fellow coders, and hit the subscribe button for more in-depth coding tutorials. Also, do follow on Instagram for the latest updates. And if you're looking for resources or have some doubts and want to discuss, join our Telegram community. See you in the next one.